Hello, I'm Mr. Craig, and I wish to work out the examples for the combustion, synthesis, and decomposition reactions. This is the first part of two different types of reaction worksheets that we're going to work out. But let's take a look at the examples. Alright, so again, we've talked about combustion reactions kind of lazily, if you want to say that, earlier on when we started balancing out chemical equations initially. This is the formal introduction. Or formal discussion where we talk about combustion reactions. And again, when we talk about combustion reactions where we have carbon, hydrogen reacting with oxygen, your products will always be carbon dioxide and water. Always. Now, there are other types of combustion reactions, but these are the only types of combustion reactions that you're going to be needed to be concerned with. Later on in AP Chemistry, we'll talk about different combustion reactions, but the key is, if it is a combustion reaction, you have oxygen reacting with something, and something is burning. So, in this case, when we talk about a combustion reaction, we're always going to use a hydrocarbon. So again, your products for something like this will be carbon dioxide and water. And the good news is, from this point on, you will be predicting all of the products, and that's what the examples that we're going to go over help you to do. So once you have that, then again, let's do our inventory. So we have our carbon, hydrogen, and oxygen. And on this side we have carbon, hydrogen, and oxygen. And here we have 6 carbon, 12 hydrogen. We have 6 plus 2 oxygen, so a total of 8. Don't forget that we have to add up all the atoms on the same side of the arrow. On this side, we have 1 carbon, 2 hydrogen, and 3 oxygen. Let's get that down just a little bit. Okay. So again, like I discussed earlier on, always try to do the water first and make sure it has an even coefficient in front of it, and then save the oxygen for last. So let's go ahead and start with that. So our hydrogen, we have 12. We need 12 hydrogen, so the best thing to do is put a 6 there. Oops, choose a different color. So we'll put a 6 here. And the good news is that is an even number, so we don't have to change that. And we do have an even number. We did it first. So we have 12 hydrogen. Let's get our inventory for our oxygens. So 6 times 1 plus 2 is 8. Alright, so let's come over here. The hydrogen looked good. So now let's balance the carbon on this side. Since we already have 6, we need to put a 6 there. Oops. That's an ugly 6. Something's going on with the board today. So 6 there. And that gives me 6 carbon. So now we have 6 times 2, which is 12, plus 6 times 1, which is 18. Okay. So my carbons and my hydrogens look good. Now I need to get 18 oxygen on this side. But when we look at it, don't forget, we do have some oxygen. They're not hidden, they're just in there. So we want to take 18, which is our total, minus the 6 that we have. That gives me 12. So 12 divided by 2 is 6. Okay, so again, easiest thing when looking at combustion reactions, the products will always be carbon dioxide and water for the type of combustion reactions that you're working with. Try to balance the hydrogens first or the water molecules first and make sure you have an even coefficient, and then save your oxygen for last. So look at the second example. Don't get flustered or upset when you see these two switched. Just remember, the plus sign just means and. So technically speaking, we have oxygen reacting with glucose, or we have glucose reacting with oxygen. It's okay. Don't get your panties in a bunch and get all upset that this is first and that's second. They're the same thing. That plus sign just means and. That these are the things that we start with. So here we have carbon, hydrogen reacting with oxygen in a combustion reaction. What are my products? I hope you said carbon dioxide and water. Okay. So again, doing the inventory, and you kind of need to do an inventory for the combustion reactions. And on this side, carbon, hydrogen, oxygen. So here we have 22. Here we have 46. And oxygen, just 2. On this side, we got 1, 2, and 3. Okay. So again, start off with your water. We have 46 over here. If we want to get 46 over here, we would put a 23, but a 23 is an odd number. So we need to not use 23, but an even version of that. So 23 times 2 is 46. So 46 times 2 is 92, I believe. If I'm doing my math right, I believe that's 92. That is 92. And so let's get our oxygen count. So 46 times 1 plus 2 is 48. Don't worry about that, that will change. Let's come over here and fix this one. So we need to double this. Whoops, not on that side. Sorry, have it. So now we have 92 hydrogens over here, which now means we have 44 carbon. So let's fix our carbon over here. So now we have 44 carbon. Let's get our oxygen. So we have 44 times 2, which is 88, plus 46 times 1. So we have 134. So we have 134 oxygens. Okay. On that side, which means that we will need 134 on this side. So 134 divided by 2, what is that? 70. Ah, shoot. Let's go old school here, guys. So 67. There we go. Sorry, had a little brain fart there. Okay, so 67. Now, looking at that, is it possible to reduce these values down any further? No. Is that ugly? Absolutely. And that's the way a lot of combustion reactions are. So don't get too upset about that. All right, looking at the second type of reactions is synthesis. So again, when you're looking at synthesis reactions, what we essentially have is A plus B, and they're coming together to form one product. So what we want to do in this case is first of all, we want to make sure we write our metal first, and then we want to put our non-metal next. That's what we have with A and B. Or if we have two non-metals together, just add them together, and we'll talk about that a little bit later on. But in most cases, these will all be ionic. So here we do have zinc, and we have nitrogen. Now, the key to this is do not bring the coefficient over, or I'm sorry, the subscript over, unless it's a polyatomic. That's the only time you copy subscripts. Here, we're just going to bring one example or representative from each. Now, zinc, again, if you look at your periodic table, zinc is right here, and it has a +2 charge. So what that means is when we look at this, we want to make sure that the zinc has a +2 charge. The nitrogen has a -3 charge. That's the charge that we're going to work with on this. And so that does not balance out to equal 0. So we need 3 of those and 2 of those. Now, once we have our formula written out correctly, now we come over, and I'm not going to do an inventory for this. We want to balance out atoms. So we have 2 nitrogen here and 2 here. Now, the reason why there's a 2 here is because of the charges, not because there's a 2 here. That's huge. Don't get in that mindset of thinking, oh, there's a 2 there, I'm going to bring it over. That won't work every single time. It does work occasionally, but it won't work every time. The zinc, we have 3 over here. We need a 3 there. If you need to do the inventory, by all means do the inventory, but I won't do it on these types of problems. All right, looking at the next one. Here we have chlorine and aluminum. Again, we're taking the generic equation is we're going to take A plus B and make AB, assuming that A is a metal and B is a non-metal. However, in this case, we have our non-metal first and our metal listed second. That's okay because we have a plus sign separating it. So you knowing that you have your periodic table in front of you, saying to yourself, okay, well, aluminum's here and chlorine's here. Hey, that's a non-metal, that's our metal. You have to be aware of that. You have to be knowingly aware of that, or actually take a look at your periodic table. So taking a look at that, we're going to write 1 of each, aluminum and chlorine. Again, that subscript is not coming over. Don't do it. So aluminum has a +3 charge, chlorine is -1. Again, looking at your periodic table, aluminum +3, chlorine -1. So when we look at this, we're not going to put a 2 there and then put parentheses around it. That just does not exist. So that means we need 3 of these. So since I have 3 chlorines, that means that I'm going to need to balance my chlorines. I have 2 here and I have 3 here, so that means I need to put a 3 there. And whoops, let's change those colors, sorry. Let's put a 3 there and a 2 there. So now I have 6 chlorines, but now my aluminum number has changed, so I need to put a 2 there. Okay? So with synthesis, take your metal and your non-metal, make sure you write it correctly. Don't you dare write chlorine before aluminum. Alright, the next type is decomposition, and the generic equation for this is you have your compound and it breaks apart into its elements. And in some cases, the elements, if it ends in INE or gen, will be diatomic, which means that you'll have 2. Which is a great example for our first one, where we have sodium and chlorine, so AB. We're going to break it down into sodium and chlorine, or chloride, but we're going to look at chlorine all by itself. Chlorine, INE, diatomic. So be sure that you write that. Don't you dare write one of those that end in INE or gen as a single element by itself. Now when it gets with something, obviously we don't carry the subscript, we want to balance charges. So let's balance this out. So we start off with chlorine, we have 2 of those. It means we have 2 of those and 2 of those. Pretty simple. Decomposition is fun. And let's take a look at the last one here. So we have calcium oxide. Again, based off of the generic equation where we have AB breaking down into a metal and a non-metal. Let's continue on with that. So we have calcium and oxygen, which ends in gen. That means O2. So when looking at this, pretty much like the other one, we have 2 there, need a 2 there, and a 2 there. Alright, in the next video, I will be working out the even problems. Hope this was helpful.